What up, people of YouTube? So it's me, and I am starting this new video series to do exactly what the title says. I'm building a rocket. I'm more than just building a rocket, though. I'm actually researching and developing a new fuel cycle for rockets for sort of the lower cost end of the spectrum. So for like mostly suborbital stuff, well, to all suborbital stuff, but anything between like a hobby rocket and say sort of an upper level sounding rocket. So in this series, we will be documenting the build process, sort of the thoughts involved in where we're going with the project and why we're doing it. Hopefully you'll get introduced to a lot of the people involved. It's just a really, really cool project, and I wanted to involve as many people as possible. Our goal is sort of our goal is to put a rocket into space, actually, 3 years from now. I want to put a suborbital payload up in space and get it back. I want to put a Lego man on the payload, because why not? That's kind of the nerd dream, I think, is to have a Lego man that's been in space. And we will be sending name tags of all of our supporters into space and returning them in little acrylic pieces. And I've got a laser cutter over here that I am going to cut them on. But anyway, this is sort of just an introduction to the process. I have some clips of me working on stuff, and I'll just kind of explain what's going on. So, yeah, thanks for watching, and I hope you enjoy.
Alright, so today I am making fins. Why fins? Well, mostly because I neglected to start filming before today, and so you're going to see me starting with fins. But anyway, there's actually a real reason why I'm making fins. As you can see, I'm making several fins on this CNC router. I'm cutting them with an 1/8 inch zirconium nitride plated end mill, 2 flutes, perfect for aluminum, and I'm using it to cut 4 different fins. That's because the actual rocket has 3 fins, and I have a 4th one that I'm going to be using for the rest of this video as a test piece. Why do I need to test a fin? Well, because I plan to TIG weld it. And anytime you're TIG welding something, you've got to worry about things moving, things changing, things shrinking, shapes changing, etc., etc. So anyway, with that in mind, I decided to start off with 4 fins and 1 test piece. Well, as I stated earlier, I am heading a research team who is developing a new rocket fuel cycle. Now, this fuel cycle is a fuel cycle that's circulated around hybrid rocket motors. Motors that received intermittent attention throughout the years and have their ups and downs, haven't really received a lot of recent attention due to the focus on reusability and orbital class rockets. And, orbital class rockets are really important, and that's certainly where most of the money is in the industry. But, a field that hasn't received a whole lot of attention is suborbital and sounding. The Origin's doing, I think, focusing on like space tourism and stuff, but what about atmospheric science? What about, microgravity research and all that? Well, for that, you need a rocket that's smaller. You need a rocket that can boost you up to several 100,000 feet or so, and then recover your payload intact. And so we're working on a fuel cycle that is going to be aimed at reusable suborbital vehicles. And fully reusable suborbital vehicles, meaning that you literally just need to refuel them and refly them. Obviously, this has kind of been a, dream or goal for a lot of projects over the years, but, sometimes it just takes a little bit of out-of-the-box thinking to make it work, and that's what this project is about. Basically, what I did was I looked at the hybrid rocket motorcycle, thought about it for a long time, studied it, took all the pieces apart, put them back together in a way that solved as many problems as I could, while not creating too many new ones. What you can see me doing here is I'm just routing a slot in a spare piece of aluminum. It's 3-inch round, 2.75 inside diameter about. You can see I was using a smaller piece of round aluminum just as a centering piece. That piece will roll into the bottom, so I can mark the center of that. It'll be pretty decently in the center of the piece. Obviously, if you were doing this correctly, you'd want to use an edge finder. I do have an edge finder. This piece isn't supposed to be the greatest piece ever. It's just a test piece to see how strong the material is and how much it moves or comes off round during welding. So anyway, I'm milling the slot with the same end mill I used on the 1/8 inch before. It's an 1/8 inch end mill, so the size of the slot and the size of the fin should match perfectly. Okay, well, that being said, let's get back to what the project's about. So, what's a hybrid rocket motor? Well, there are basically 3 major different groups of rocket engines. You probably know this if you know anything about rockets, and to avoid me insulting your intelligence, you can just skip ahead if you already know everything about, rocket motors, whatever. But anyway, let's start off with the basics. What are the three main types of rocket motors? Well, you've got solid rocket motors, you've got liquid rocket motors, and then of course you've got hybrids. There's a lot of other types of propulsion that you can use out in space. There's magnetoplasma-dynamic propulsion, there's solar electric propulsion, there's Hall effect thrusters, there's ion thrusters, which are similar to Hall effect thrusters, which work a little differently. There's variable Vasmir, there's solar sails, there's photon rockets. I mean, there's all kinds of different stuff you can come up with, but for getting off the ground, you need something that has a very high thrust-to-weight ratio and also has very good efficiency in the atmosphere as well as in space. And obviously that means that the outlet pressure from your rocket motor has to be equal to or greater than the atmospheric pressure. Otherwise, I'm sorry, you don't have a rocket. You have, well, something else that's not going to go very far. Anyway, so solid rocket motors. You're familiar with them, even if you don't know that you are. They're often used as boosters. They're often used as first stages. They're often used in low-cost or low-fidelity rockets where efficiency is of utmost importance and cost and reliability is, such as missiles, military weapons, fireworks, things that are just designed to work once and just always work. Okay, so solid rocket motors. They use a solid fuel and a solid oxidizer blended together in an epoxy-like compound that you can then form into whatever shape you need with specific interior geometry that you can optimize for things like burn rate, regression rate, chamber pressure, nozzle ratio, all these sorts of things go into designing solid rockets. But usually the beauty of solid rockets is that once the sort of science is done, you can just repeatedly make them. You can make a lot of them. They're all going to work the same. If one works, all of them are going to work. The disadvantage is, though, you can't shut them off once you've started. You can't relight them. You can't throttle them. And, of course, you can't reuse them. So, with that said, what's a liquid rocket motor? Well, a liquid rocket motor is exactly what it says. It uses liquid fuel. It uses a liquid fuel and a liquid oxidizer. Traditional liquid fuels are hydrocarbons like alcohol, kerosene. Newer cycles even use methane because it has much better chemical combination efficiency than other fuels. So even though the actual fuel has lower impulse, when you add together the fact that it burns more efficiently and more cleanly, you end up with better impulse. Now let's talk about sort of the numbers that you use to quantify rocket motors. You've got basically three numbers. You have total impulse, you've got average impulse, and you've got specific impulse. And they're all functions of each other. So, total impulse, that is the total amount of change in energy that a rocket motor can deliver. Impulse is just force times time, so Newton seconds is usually a pretty good way of classifying the total energy that a rocket can produce. Okay, then there's average impulse. Average impulse is a measure of force. It tells you how much force a rocket motor produces in a given amount of time, and this is normally measured in newtons or kilonewtons. Obviously, there are other ways to measure it. But, so, then there's the third, that's specific impulse, and that's a measure of efficiency. Any of you who are into engineering or, any type of physics know that when you hear the term specific, you're talking about something that's relative to the fuel and not the system as a whole. So specific impulse is exactly what it sounds like. It is the energy per unit mass, or more specifically, the time in seconds that 1 pound of fuel will produce 1 pound of thrust, or 1 kilogram of fuel. It's a dimensionless quantity measured in seconds. Okay, in this next clip, you're going to see me, well, not me, a good friend of mine, Daryl, he's a professional welder. He works in my shop. He's TIG welding this up, and this is my horrible attempt to video it through a welding helmet. Anyway, so, impulse. How do you design a rocket motor? Well, first you've got to decide how much total impulse you need. And then you got to decide, well, do you need all that impulse immediately? Do you need it over a long period of time? Or do you care more about the efficiency of the fuel? Are you trying to go between planets and you can only carry a very little bit of fuel with you? There's a lot of considerations to go into designing a rocket motor. So, with that being said, the third type of rocket motor, hybrid rocket motors. What's a hybrid rocket motor? Well, by definition, a hybrid rocket motor is just any rocket motor that uses its fuel and oxidizer in 2 different phases. So, for instance, a solid fuel, a liquid oxidizer, a liquid fuel, a solid oxidizer, all of the seconds. It's only really seen in some research labs and papers. The most common way to do a hybrid rocket motor is a solid fuel grain and then a gaseous oxidizer stored as a compressed or self-cooled liquid usually, or liquid oxygen, in which case that requires a lot more complex plumbing, etc., etc. A typical fuel that you would see with a hybrid rocket motor is HTPB, or hydroxyl terminated polybutadiene. That's a mouthful. Or paraffin wax. Actually, there's a bunch of research recently that's been done on paraffin wax, and I'll get back to that later. But anyway, why would you use a hydrocarbon like HTPB? Well, a couple reasons. First of all, it is a thermoplastic. This means that you can melt it easily. similar to a 3D printer and reform it as it was originally, and it will not lose its chemical properties. This makes it easy for making fuel grains with. Also, it's very cheap and has a very high energy density relative to its cost. And that is the most important metric for what we're going to get into discussing. And when you're talking about designing a cheap rocket motor, you don't care about having the most efficient, the most powerful, the best rocket fuel. You care about having the fuel that is the cheapest to get where you need to go, essentially. So, and so in this video I'm just running off the fillets that were welded up with a ball end mill. This is the radius that I want to cut it with. This took a little bit of figuring out how to get the radiuses equal on both sides, but I figured out a pretty easy way to get them both done the same size, and that's just by rotating and move. You'll see how I do it. Okay, so hybrid rocket motors. Why? What's the point of a hybrid rocket motor? Well, a couple things. First of all, as I said before, it's traditionally very cheap. Does not cost very much. When compared with a liquid rocket motor, it's going to be compared in cost to a solid rocket motor. Although in our case, we're actually going to be able to make them cheaper, and you'll see why. Okay, so why a hybrid? Well, a hybrid has some of the advantages of a liquid rocket motor. While not as distinct, it can be restarted in flight. In theory, it can be throttled. And most importantly, it can use a wide range of fuels, and it can also use an oxidizer that's much easier to work with than, for instance, liquid fueled oxidizer or solid fueled oxidizers. Now, obviously, most hybrids use simple pressure-fed systems because liquid rocket motors traditionally use turbo pumps or some form of cycle that pumps fuel through the motor by burning some of the fuel that you're using in a separate pre-burner that either preheats and pumps the fuel. And just like the RS-25 on the space shuttle, you've got really complicated and incredible fuel cycles that actually use the heat from the rocket engine itself to actually preheat the fuel at the same time cooling the rocket motor. Or you have systems like the F-1 rocket, where you inject the pre-burned fuel along the outside of the little inside edge of the nozzle to keep it cool with a fuel-rich mixture while running a stoichiometric ratio into the actual motor. Okay, hybrid rockets though. What are the disadvantages? Well, there are a ton of them. The primary disadvantages of hybrid rocket motors are regression rate, OF ratio, that's the oxidizer to fuel ratio, and just general difficulty of getting them to work reliably. Why? Well, think about it. A hybrid rocket motor does not have any oxidizer in the actual fuel itself. Well, what's that matter? Well, since you have no oxidizer in the actual fuel itself, you've got to get the fuel and oxidizer to combine in the combustion chamber by getting the solid fuel to evaporate and getting the oxidizer to burn well. So all that said, you can see there are some pretty obvious disadvantages, and in this entire series we will be working through how we solve those disadvantages. So thank you for watching. Please come back later, and so I'm just sanding off these parts to finish them. And goodbye! Oh, you can also like and subscribe if you want to do that, but